Here we are going to complete an exam question on electric fields. Pause the video now and try all parts of this question. Part A says draw an arrow on figure 3.1 to show the direction of the electric field at point A. So the electric field is always defined as the direction a positive charge will move. So here, if we put a positive charge here, it will go towards the negative terminal. So it should be directly to the left. Determine the kinetic energy in electron volts of an electron at the anode. So when the electron has travelled from here all the way over here. So you'll see that it's been accelerated through a potential difference of 1500 volts. So we need to be clear that the work done is the potential difference times charge, but that would give us the energy in joules. So what this is really saying is it was a bit of a trick question almost, in that the answer is just 1500 because the 1 electron volt is the energy gained by 1 electron traveling through a potential difference of 1 volt. If we have 1 electron traveling through a potential difference of 1500 volts, then it's going to gain 1500 EV. So this one here, we want to use the work done is equal to half mv squared, but here we do want the energy in joules. This must be in joules. So we need to use this equation here, potential difference times charge, to get our energy in joules. So now it's just a case of plugging in the numbers. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. V is obviously 1500 volts. Q is the charge on the electron, 1.6 times 10 to the minus 19. When you rearrange that and plug the numbers in, you get 2.3 times 10 to the 7 meters per second, which does seem high, but that does appear to be the answer. Okay, question C is all about the electron carrying on and entering a region of both an electric field and also a magnetic field, and it tells you about the information about the magnetic field here. Derive an expression for V in terms of E and V. This is a classic question that comes up all the time. What you have to realize is the electric field is obviously down, so the electron is going to feel a force in one direction. If it's an electron, then it would actually feel a force up. So why is it going straight? Well, it feels a force down due to the magnetic field. So we're balancing the magnetic and electric fields. So then the forces are balanced. The electric force is QE and the magnetic force is BQV. The Q's obviously cancel, and then we end up with V is E over B. The magnetic flux density is increased further. The electric field strength is unchanged. Describe and explain what happens to the path of the electrons. So what happens? We've got the electric force, which is QE. So this remains constant. So the electric force is unchanged. The magnetic force is BQV. This is increased. So this isn't going to get you any marks. I'm just summarizing the information so far. But what will happen? Well, we've said the magnetic force is acting downwards, and that's increased. So there will be a greater force or more force acting down. And I might just say, to be safe, the same force acting up. So the electron's path is bent down. Okay, the electron will feel more force going down, and so it will do something like this.